Have you ever stopped to think about the sheer ingenuity packed into keeping an aircraft engine firing flawlessly and, well, the lights on?
It's pretty amazing when you dig into it.
Yeah, I was fascinated when I started digging into this chapter you sent on ignition and electrical systems. I'm really keen to understand the core of it with you today.
Okay.
So this deep dive, it's all about making sense of the essential knowledge around reciprocating engine ignition. Both the classic magneto systems and the modern FADE.
Right, and the generators too.
And how those reliable DC generators keep the power flowing. We want to give everyone listening the insights into how these systems operate and why their upkeep is absolutely vital.
Exactly. You've given us a great set of material, and our mission today is to pull out the really critical information without getting too bogged down.
Sounds good.
We'll explore how these reciprocating engines get that precisely timed spark, looking at both magneto and FADE technologies. Then we'll dive into the world of DC generators and, their role in keeping an aircraft's electrical systems running smoothly.
Okay, let's get straight to the heart of it then. The ignition system in a reciprocating engine, what's the absolute fundamental job it has to perform?
At its core, the ignition system has one non-negotiable task. It must deliver a high-tension spark across the electrodes of the spark plug in each cylinder.
My tension spark. Got it.
And it has to do this in the correct firing sequence at a very precise moment, like a specific number of degrees before the piston reaches its top dead center.
Ah, so timing is everything.
That pinpoint accuracy in timing is what dictates efficient and powerful combustion. Absolutely crucial.
And the chapter you shared lays out two primary ways this is accomplished, right? We're talking magneto ignition systems and the more modern electronic FADC systems.
That's right.
Plus, it looks like magneto systems have their own subcategories.
Exactly. The two main ways are magneto ignition and full authority digital engine control, or FADC.
FADC.
And yeah, within the magneto world, we also see single and dual magneto designs. Older setups often use two separate single magnetos for redundancy.
Makes sense. Two is better than one.
Right. Whereas a dual magneto houses two complete ignition systems within a single unit, but they share a rotating magnet.
Interesting. So let's start by unwrapping these magneto systems. The name itself hints at magnets, obviously. How does this engine-driven device actually generate that spark we need?
Well, what's remarkable is that a magneto is a completely self-contained, engine-driven AC generator. It uses a permanent magnet as its initial power source.
Self-contained, so it doesn't need the plane's battery to start.
Not for the spark itself, no. That's the beauty of it. The basic principle relies on just three key elements: a permanent magnet to establish a magnetic field, a coil of wire, and relative movement between these two.
Okay, so the engine's rotation spins this magnet, and that somehow induces electricity in the wire coil. It sounds a bit like magic.
It kind of does, yeah. As the engine turns the permanent magnet, it causes the invisible lines of magnetic force, what we call magnetic flux, to cut across the coil windings.
Right.
The more lines that cut across, the stronger the electrical current produced. This induced current then creates its own magnetic field around the coil.
Okay.
Now, the real trick happens when this current flow is abruptly interrupted.
Interrupted? How?
We'll get to that. But when it stops, the magnetic field collapses rapidly across a second set of windings within the coil, and this sudden collapse generates a very high voltage pulse. We're talking thousands of volts needed to jump across the spark plug gap.
Wow. So interrupting the first current creates the big spark voltage.
Precisely. It's all about that rapid change.
It sounds almost like a precisely choreographed electrical event happening inside. The chapter also mentions three distinct circuits within a high-tension magneto system: magnetic, primary electrical, and secondary electrical. Why is it helpful to think of it in these terms?
Well, breaking the magneto down into these three circuits isn't just for theoretical understanding. It really helps us pinpoint where potential issues might arise.
Ah, for troubleshooting.
Exactly. It's like a weakening permanent magnet. That would affect the magnetic circuit, the initial energy. Problems with the breaker points would impact the primary electrical circuit, the one that gets interrupted.
Okay.
And faults in the high voltage wiring or distributor would be in the secondary circuit. So understanding these divisions is really key for effective troubleshooting and maintenance.
Right. And for a spark plug to actually fire at that critical moment when the piston is in the right position, the text highlights three basic events that must happen simultaneously. What are those crucial steps?
Yes, for a spark to occur at the correct instant, three things must align perfectly. First, the magneto's rotor must be in the E-gap position.
E-gap.
E-gap. It stands for efficiency gap. This is where the magnetic field is at its absolute peak strength and optimally aligned for a rapid change.
Got it. Peak magnetic change potential. What's second?
Second, the breaker contact points in the primary circuit must open to abruptly halt that current flow we talked about.
Ah, there's the interruption.
That's it. And third, the distributor must be correctly aligned to direct the resulting high-voltage pulse to the specific spark plug in the cylinder that's ready to fire.
Okay, E-gap, points open, distributor aligned. The E-gap position sounds incredibly important. Why is that exact timing so critical for the system's operation?
Well, what's critical about the E-gap position is that it represents the point of maximum rate of change of magnetic flux.
Maximum rate of change. Okay.
So when the breaker points open at this precise moment, it allows the magnetic rotor to very quickly reverse the magnetic field passing through the coil core.
A rapid flip.
Exactly. And this rapid flip of the field is what induces that powerful high-voltage pulse in the secondary coil. The faster the change, the higher the voltage generated.
So being slightly off E-gap really matters.
Oh, definitely. Being just a few degrees off this optimal E-gap isn't just a minor inefficiency. It could mean the difference between a strong, reliable combustion event and a weak, unreliable one. It directly impacts engine power and fuel efficiency.
And these breaker contact points, they're the gatekeepers for that initial current flow. How do they open and close in perfect synchronization with the engine's rotation?
The precise opening and closing of these points is orchestrated by a breaker cam. It's mechanically driven by the engine.
Okay, a cam.
This cam has lobes, usually 2, 4, or maybe even 8, depending on the magneto's design and the number of engine cylinders.
Right.
As the cam rotates, these lobes push against a little lever, causing the contact points to open, and then springs pull them close again. This opening and closing is timed very carefully relative to the rotor magnet's neutral positions.
To hit that E-gap moment.
Exactly, ensuring the points open when the magnetic flux is changing fastest.
The chapter also mentions a condenser working in conjunction with these breaker points. What crucial role does that component play in this rapid interruption of current?
The condenser is a vital partner to the breaker points. You see, when the points snap open, the sudden stop of current in the primary coil could actually cause a spark, an arc, to jump across the opening points.
Like a little leftover spark.
Yeah, and that arcing would slow down the interruption of current, which would reduce the energy available to create that high-voltage pulse in the secondary coil.
So it would weaken the main spark.
Right. The condenser acts like a temporary electrical sponge. It absorbs the energy from the collapsing magnetic field in the primary coil just for a moment.
Okay.
This prevents that arcing across the points and ensures a very rapid, clean break in the current flow. This abrupt stop is what leads to the powerful voltage spike in the secondary.
Clever. Okay, so we've got this massive voltage spike generated. Now, how does that get channeled to the correct spark plug at the precise moment? That's where the distributor comes into the picture, right?
Exactly. The high-voltage pulse produced in the secondary coil is fed into the distributor.
Right.
The distributor has a rotating arm, the rotor, and a stationary cap, the distributor block.
Like in a car, sort of.
Very similar principle, yeah. The rotor has a conductive strip embedded in it, and it spins in sync with the engine's firing order. As it spins, the rotor tip aligns momentarily with metal contacts embedded in the distributor block.
And each contact goes to a plug?
Yep. Each of these contacts is connected to an ignition lead that goes to a specific spark plug. So as the rotor sweeps past each contact in turn, it delivers that high-voltage jolt to the cylinder that's next in the firing sequence.
This whole system sounds quite precisely engineered, and the chapter emphasizes that things like moisture and condensation can really disrupt this delicate process. Why is moisture such a significant threat?
Moisture is a major enemy of any high-voltage electrical system, really, because water conducts electricity even if it's not a perfect conductor. So if moisture gets into the insulating parts of the magneto and distributor, like the distributor block, coil windings, or around the high-voltage terminals, it can create unintended pathways for the electricity.
Short circuits, basically.
Well, not quite a dead short, but instead of the high-voltage current taking the intended path across the spark plug gap, it can flash over across this damp insulating surface to ground or maybe to another terminal.
Flash over. Okay.
And that leads to misfires. It can even cause more serious issues like pre-ignition or potentially engine damage if it's bad enough.
And this flashover can leave a permanent consequence. I read about something called carbon tracking.
Yeah.
What exactly happens there?
Yeah, what's insidious about flashover is the heat. The intense heat of that electrical discharge can actually burn any dust, oil, or fuel residue on the insulating surface.
Okay.
And it leaves behind a very fine conductive path of carbon. That's the carbon track.
Like a pencil line, almost.
Exactly like that. And once this track forms, even if the moisture dries up later, the high-voltage spark will preferentially follow this low-resistance carbon path to ground rather than jumping across the spark plug gap.
So it permanently weakens or stops the spark to that cylinder?
Pretty much. It effectively disables that cylinder's ability to fire until the affected component is cleaned thoroughly or, more likely, replaced.
So what preventative measures do they take to combat this moisture problem in the first place? The chapter mentions things like waxing and venting of components.
Right. So to minimize moisture absorption, components like the coils, condensers, distributors, rotors, they're often treated with a special wax during manufacturing.
Wax? How does that help?
The wax causes any moisture that does condense to form into isolated beads, rather than spreading out into a continuous film that could create a conductive path.
Ah, clever. Makes it harder for the electricity to follow the water. Exactly. Additionally, magnetos and distributors are typically vented. This helps manage internal temperature fluctuations and equalize pressure. That's especially important at higher altitudes, where the lower air pressure makes it easier for sparks to jump across surfaces to flash over.
Right, lower pressure, easier arsing.
Venting helps to maintain a more consistent internal environment, reducing that risk.
So keeping those vents clear of any blockages seems absolutely crucial then for reliable operation.
Oh, absolutely critical. And the chapter also points out, importantly, that the air circulating through the ignition system needs to be clean and, crucially, oil-free.
Oil's bad too.
Yeah, even a thin film of oil on ignition components can significantly increase the likelihood of flashover and subsequent carbon tracking.
Got it. Keep it clean, keep it dry, keep it vented. Now let's shift our focus slightly to the wiring itself, the ignition leads. I noticed the chapter mentioned capacitance and the use of shielded leads, and even the practice of reversing plug polarity during maintenance. What's the reasoning behind all of that? Okay, yeah. Ignition leads, like any conductor separated by an insulator, have some electrical capacitance. They can store a small electrical charge.
Okay.
Shielded leads, which have that braided metal sheath around the high-voltage wire, are essential mainly for minimizing radio frequency interference, RFI.
So it doesn't mess with the radios and avionics?
Exactly. But this shielding inherently increases the capacitance of the lead.
Okay. And the polarity reversal.
Right. So to even out the wear on the center and ground electrodes of the spark plugs, because one tends to erode slightly faster depending on the polarity of the spark.
Oh, interesting.
Yeah. So a common maintenance practice is to periodically reverse their polarity by swapping their locations between cylinders, or sometimes pairs of leads are swapped at the magneto. This helps ensure more uniform erosion of the electrode materials, extending plug life.
Makes sense. And the construction of these shielded leads?
Typically, you've got a central conductive core, surrounded by thick silicone insulator for high voltage protection, then the woven metal shielding braid we mentioned for suppressing interference, and finally, an outer layer, often silicone rubber, for environmental protection.
Okay. And what about the ignition switch in the cockpit? It sounds like it doesn't operate like a typical household on-off switch.
You're absolutely right. The ignition switch in an aircraft magneto system has a unique safety feature. In the OFF position, it actually completes an electrical circuit to ground.
Completes it? So off means connected.
Exactly. It grounds the primary circuit of the magneto. This prevents the magnetic field from collapsing properly across the secondary windings when the points open, thus stopping the generation of any high-voltage sparks. It's a fail-safe way to kill the engine.
Right. So no spark possible when it's grounded?
Correct. Then in the IN position, the switch simply opens this ground connection. That allows the breaker points to control the interruption of the primary current normally, leading to the production of sparks.
Got it. Off grounds it, on ungrounds it. The chapter also delves into auxiliary starting systems for magnetos, things like booster coils, impulse couplings, and starting vibrators. Why are these necessary, especially given the magneto is supposed to be self-powered?
Good question. These auxiliary systems are specifically designed to help start the engine when it's being cranked at low speeds by the starter motor.
Because the magneto isn't spinning fast enough yet?
Precisely. At those lower rotational speeds, the magneto itself might not spin fast enough to generate a spark that's sufficiently strong and consistently timed to reliably ignite the fuel-air mixture.
Okay, so what does a booster coil do?
The booster coil, which you primarily find in older, larger radial engines, is basically an external coil. When it's activated during starting, it uses the aircraft battery's power to produce a series of high-voltage sparks independently of the magneto's rotation speed. These sparks are then distributed to the cylinders in their firing order via the magneto's distributor.
Ah, so it provides its own hot spark just for starting?
Essentially, yes.
Yeah.
A shower of sparks.
And the impulse coupling. I remember reading about a distinctive clicking sound during engine cranking.
Ah, yes, the clicking.
Yeah.
The impulse coupling's a really clever mechanical mechanism, usually built directly into the magneto drive.
Mechanical, okay.
At low cranking speeds, it uses a spring and flyweights to momentarily hold back the rotation of the magneto's internal magnet. And then it suddenly releases it.
So it snaps forward.
Exactly. It makes the magnet spin much faster for a brief instant than the engine crankshaft is turning. This rapid rotation generates a much stronger spark for easier starting.
Clever. Does it do anything else?
Yes. It also retards the spark timing during this process. It delays the spark slightly.
Why delay it?
It's safer for starting. It ensures the combustion event happens just after the piston has passed top dead center, which reduces the chance of kickback and puts less strain on the engine during start.
And that clicking sound.
That characteristic clicking noise you hear during slow cranking is the sound of the impulse coupling's spring winding up and the pawls engaging and releasing as the engine turns slowly.
And then it stops clicking once the engine starts.
Right. Once the engine fires and reaches a certain RPM, centrifugal force causes the flyweights within the coupling to swing out, disengaging the mechanism. The magneto then operates with its normal advanced timing.
Okay. And finally, there's the starting vibrator and retard breaker magneto system. How does that approach assist with engine start?
This system, often seen in lighter aircraft engines, uses a starting vibrator. It's an electromagnetic device, kind of like a buzzer.
Okay.
It rapidly interrupts a low-voltage DC current from the aircraft's battery. This pulsating current is fed into the magneto's primary coil.
Instead of the breaker points interrupting it.
Correct. During start. This induces a continuous shower of sparks from the secondary winding, which get distributed to the cylinders.
A shower of sparks, like the booster coil?
Similar effect, yes. Simultaneously, a separate set of breaker points within the magneto, called retard breakers, provides a spark that is timed later in the compression stroke, a retarded spark.
Ah, retarded spark again for safer starting.
Exactly. So this combination of shower sparks and retarded timing helps with starting.
Right.
In some light aircraft, this retard breaker function negates the need for a separate impulse coupling.
Okay, that's a really comprehensive look at magneto ignition systems. Very mechanical, very precise. Now let's switch gears and talk about the more modern FADDC systems. The chapter describes them as being quite a different beast altogether.
Oh, they are indeed a significant departure. FADTC, Full Authority Digital Engine Control. It's a solid-state digital electronic system. It takes over the complete management of both ignition and fuel injection.
Oh, no. Wow.
Yeah. In fact, the only moving part within the FADDC system itself is typically the fuel injector valve.
So no more mechanically driven magnets and breaker points and cams to worry about with FADT.
Exactly. Gone. FADT relies on sophisticated computer processing. It continuously monitors a whole range of engine operating parameters.
Like what?
Oh, RPM, manifold pressure, temperatures, throttle position, lots of things. And then it precisely controls the ignition timing, the fuel-air mixture, and the fuel delivery based on all that data.
So it integrates everything.
Totally integrated control. It eliminates the need for traditional magnetos, and importantly, it also eliminates the pilot's manual control of the fuel-air mixture. The computer handles it all.
How does FADEC achieve that precise ignition timing without a direct mechanical link to the engine's crankshaft, like the magneto has?
The heart of the FADEC system is the Electronic Control Unit, or ECU. It's essentially a powerful onboard computer, or often two of them for redundancy.
The brains of the operation.
Definitely. This ECU receives a constant stream of signals from various sensors monitoring critical engine parameters like crankshaft speed and position, manifold pressure, air temperature, cylinder head temp.
All that data we mentioned.
Right. Based on this real-time data, the ECU uses pre-programmed algorithms and complex maps stored in its memory. It calculates and commands the optimal ignition timing for every stage of engine operation, from starting right up to full power.
And it just tells the coils when to fire.
It sends precise electronic signals to the ignition coils to fire the spark plugs at exactly the right moment for each cylinder.
I noticed the chapter mentions a low-voltage harness connecting all the key FADC components. What are the essential parts that this network links together?
Yeah, that low-voltage harness is like the nervous system for FADEC. It carries power and data signals between the ECUs and the aircraft's main electrical bus, the ignition switch, and all those various sensors we talked about.
Okay.
Plus the control signals going out to the fuel injectors and the ignition modules. It connects everything together.
And these ECUs seem to be the brains of the FEDEC operation, as you said. How do they specifically manage the ignition for each of the engine cylinders? Is it one ECU per engine?
Typically in, say, a 4- or 6-cylinder engine, you'll often have 2 ECUs, sometimes called lanes or channels, and often one ECU might be primarily responsible for managing a pair or maybe 3 cylinders.
Okay, splitting the workload.
Yes, but the key here is redundancy. To ensure maximum reliability, each ECU, or each control channel within the FADE system, often contains independent microprocessor-based control circuits.
So like backups built in.
Exactly. Under normal operation, maybe one channel controls ignition and fuel for cylinder 1, another for cylinder 2, and so on. But if one channel were to experience a failure,
the other one takes over.
The other channel, or the other ECU, is designed to automatically take over and manage all the cylinders, providing a critical layer of redundancy. This kind of redundancy isn't just sophisticated engineering, it's absolutely fundamental for flight safety.
Yeah, you can't just pull over if your engine quits.
Precisely. An ignition failure in flight has far more critical consequences than in a car. This layered redundancy is a core safety feature.
Redundancy definitely sounds like a key design principle in FADT. What kind of sensors feed information into these dual ECUs or channels?
The ECUs rely on a really comprehensive suite of sensors to get a complete picture of what the engine's doing and its environment. You've got sensors for crankshaft speed and position, fuel pressure, manifold air temperature, cylinder head temperature, CHT, exhaust gas temperature, EGT.
A lot of inputs.
A huge amount. And crucially, many of these critical sensors are themselves designed with dual redundancy.
2 sensors for the same job.
Often, yes. So you might have 2 separate CHT sensors, for example. One sensor might connect to a control channel in ECU A, and the other sensor connects to a channel in ECU B.
So if one sensor fails,
the system can still rely on the reading from the other one. And in the unlikely event that both sensors of a redundant pair were to fail, the FADEC system is even programmed to use predetermined default values, like a safe backup mode, to ensure continued safe operation.
Impressive fallback planning. Now, the chapter mentions a PowerLink ignition system as part of FADEC. What are its main components, and how does it ultimately deliver the spark to the cylinders?
Right, the PowerLink system is often the part that actually creates and delivers the spark in a FADE setup. It typically consists of compact, high-voltage ignition coils, sometimes mounted directly on top of each ECU or near the plugs, a specialized high-voltage harness, and usually 2 spark plugs per cylinder.
2 plugs per cylinder, like dual magnetos.
Similar redundancy idea, yes. Each ECU, or channel, controls the ignition spark for its assigned cylinders. Within the ECU, the control channel commands integrated coil packs.
Okay.
Each coil pack then generates a high-voltage pulse that's directed, often, to 2 spark plug towers on the cylinder head. What's interesting is that often one spark plug tower receives a positive polarity pulse, while the other gets a negative polarity pulse.
Alternating polarity, why?
It seems to help improve the efficiency of the combustion process, and also helps extend spark plug life by balancing the electrode wear, similar to swapping leads in a magneto system.
Ah, okay. And the high voltage harness.
That just carries these powerful electrical pulses from the coils to the spark plugs themselves. Needs to be robust, obviously.
Finally, FADC seems to be closely linked to the cockpit through the engine indicating a crew alerting system, or EECAs. What kind of information and functionality does that interface provide to the pilot?
The EECAs is basically the pilot's window into the engine's health and performance and other aircraft systems too.
The screens in the cockpit.
Exactly. It displays real-time data on key engine parameters, RPM, temperatures, pressures, fuel flow, etc. And critically, it provides immediate warnings and cautions if any anomalies or system failures are detected.
So it flags problems.
Immediately. In context of FADC, Aviation allows the pilot to see how the digital engine controls are operating, confirm they're active, and it will display any faults within the FADC system itself if they've been identified by the system's self-diagnostics.
Does it help with maintenance too?
Yes, ABCs often incorporates built-in test equipment, BITE, that maintenance technicians can use on the ground for system diagnostics and troubleshooting.
Handy.
Very. The system can even record engine parameters during flight if a problem is suspected, providing valuable data for post-flight maintenance and analysis.
It's quite a stark contrast, isn't it? The mechanical elegance of magnetos versus the digital sophistication of FADC.
Completely different philosophies, really, but both aiming for reliable ignition.
Now let's move on to another absolutely crucial electrical system in an aircraft. DC generators. What is their fundamental purpose?
Pretty simple, fundamentally. The purpose of DC generators in an aircraft is twofold. Recharge the aircraft's battery and provide electrical power to all the various electrical equipment and systems on board while the engine is running.
So they keep the lights on and the battery topped up?
Exactly. They are the primary source of electrical energy once the engines are operating.
The chapter outlines three main types of DC generators based on how their field windings are configured. Can you give us a brief overview of these different connection methods?
Sure. We have series wound, parallel wound, which is also known as shunt wound, and series parallel wound, or compound wound generators.
Okay.
The key distinguishing factor among these types is the way the field windings. Those are the coils of wire that create the magnetic field needed for generating electricity.
Right, the electromagnet part.
Yeah. It's how those field windings are electrically connected in relation to the armature, that's the rotating part where voltage is induced, and the external electrical circuit of the aircraft.
The text pretty quickly dismisses series wound generators as unsuitable for aircraft applications. What's the core reason behind that?
Series wound generators suffer from a major limitation. Very poor voltage regulation under varying electrical loads.
Voltage swings around too much.
Exactly. In this design, the field winding is connected in series with the armature and the external circuit. So, as the electrical demand, the load changes, the amount of current flowing through the field coils also changes.
Okay.
A higher load draws more current, which strengthens the magnetic field and increases the output voltage. A lower load reduces the current and the voltage drops. This wild fluctuation in voltage just isn't stable enough for sensitive aircraft equipment.
Right, you need steady voltage. So shunt wound generators are a more common choice for aircraft then. How do they operate differently in terms of field winding connection?
Yeah, shunt is more common. In a shunt wound generator, the field winding is connected in parallel, or in shunt, with both the armature and the external electrical circuit.
Okay, parallel connection.
This configuration provides much better voltage regulation than a series wound generator. However, the output voltage of a shunt wound generator will still tend to decrease slightly as the electrical load increases and increase slightly as the load decreases.
Still not perfectly stable.
Not perfectly, no. To compensate for these variations and also to allow for voltage adjustments, traditionally a rheostat, a variable resistor, could be placed in series with the field windings.
To tweak the field current.
Right. Controlling the field current influences the magnetic field strength and thus the output voltage. In modern aircraft, though, this manual adjustment is typically replaced by automatic voltage regulators that do this job electronically and much more precisely.
Okay. And the third type, compound wound generators. How do they combine the characteristics of series and parallel windings to achieve more stable voltage output?
Compound wound generators are designed to sort of get the best of both worlds. They incorporate a shunt field winding connected in parallel, like we just discussed, and also one or more series field windings connected in series with the armature and the load.
So both types of windings?
Both types. The current flowing through the series field windings is directly proportional to the load current. This current creates an additional magnetic field that helps to counteract the voltage drop that normally occurs in shunt wound generators as the load increases.
Ah, the series part boosts the voltage under load.
Exactly. By carefully designing the number of turns in the series field winding, manufacturers can create compound wound generators that maintain a relatively constant output voltage across a wide range of electrical loads. That makes them really well suited for the demanding electrical systems of many aircraft.
Okay, that makes sense. When we're discussing DC generators for aircraft, what are the crucial ratings that one needs to be aware of when considering a specific unit?
The two primary and most important ratings for a DC generator are its nominal voltage and its maximum power output.
Voltage and power.
Right. The voltage rating, typically either 14 or 28 volts in most general aviation aircraft, must match the aircraft's electrical system. It's usually designed to be slightly higher than the battery voltage, 12 or 24 volts respectively, when fully charged to allow the battery to charge.
Okay. Needs to be higher to push current into the battery.
Correct. The power output is specified as the maximum number of amperes or amps the generator can safely and continuously supply.
So the current capacity.
Yes. When it comes to replacing a generator, it's absolutely essential to select a unit with the exact correct voltage and at least the same, if not maybe slightly higher, amperage rating to meet the aircraft's electrical demands without being overloaded.
The direction of rotation of the generator is also mentioned in the chapter. Why does it matter whether a generator spins clockwise or counterclockwise?
Yes. The direction in which the generator armature rotates, as viewed from the driven end, the end connected to the engine gear train,
Yeah?
that direction directly determines the polarity of the output voltage, positive and negative.
Oh, right. So spinning the wrong way reverses the voltage.
Exactly. It's absolutely critical to use a generator with the correct direction of rotation for the specific aircraft installation. Installing a generator designed for the opposite rotation will result in reversed voltage output, which could potentially damage sensitive electrical and electronic components in the aircraft.
Definitely want to avoid that. How do you know which way it should spin?
The correct rotation direction is usually clearly indicated on the generator's data plate.
Yeah.
Clockwise, CW, or counterclockwise, CCW.
Okay. And what's the significance of the coming in speed that the chapter refers to in the context of generators?
Coming in speed is basically the minimum rotational speed at which a DC generator will start to reliably self-excite and produce its normal rated output voltage.
Self-excite.
Yeah, using the residual magnetism in its field poles to start the generation process. Anyway, aircraft engine speeds vary a lot, from idle to maximum power. The generator drive system is typically geared so the generator spins faster than the engine, maybe somewhere between 1/18 and 1/12 times the crankshaft speed.
Okay.
The coming-in speed for most aircraft DC generators is generally around 1,500 RPM or so. Below the speed, the generator might not produce enough voltage to charge the battery or effectively power the aircraft's electrical loads. You might see the ammeter showing a discharge at very low idle speeds.
Ah, okay. So it needs a certain minimum speed to start working properly. So what kind of routine maintenance is typically required for DC generators to ensure they continue operating reliably in an aircraft?
Regular maintenance for DC generators includes things you might expect. Periodically checking the physical security of the generators mounting to the engine.
Make sure it's not loose.
Right. Carefully inspecting all electrical connections for tightness, cleanliness, and any signs of corrosion. The exterior of the generator should be kept clean and free from dirt, grease, and especially oil.
Oil's bad here too.
Very bad. The presence of oil often indicates a leaking engine oil seal nearby that needs to be fixed because oil can damage the generator's internal insulation.
Okay. What else?
The condition of the generator brushes is also crucial. They wear down over time. They should be inspected for wear, proper length, and making good contact with the commutator.
The commutator. That's the rotating part the brushes rub against.
Exactly. It's the segmented copper ring. And finally, the overall electrical operation of both the generator and its associated voltage regulator should be verified at regular maintenance intervals according to the aircraft's maintenance schedule.
The brushes inside the generator seem to be a critical wear item. The chapter describes the process of seating new brushes using fine sandpaper. Why is this step important, and what precautions should be taken during this procedure?
Yeah, proper contact between the generator's carbon brushes and the copper bars of the commutator is absolutely essential for efficient current transfer.
Makes sense.
New brushes often have a flat or slightly irregular contact surface out of the box, and they might not perfectly match the curvature of the commutator.
So seating makes them fit perfectly.
Exactly. The process of seating the brushes involves gently using very fine grit sandpaper, like 1000 grit or finer, to wear the brush face until it conforms precisely to the commutator's curved surface.
How do you do that?
You place the sandpaper between the brush and the commutator with the abrasive side facing the brush, hold the brush down with normal spring pressure, and then rotate the armature by hand in its normal direction of operation.
Okay.
This ensures maximum contact area, which minimizes electrical resistance, reduces heat generation, and prolongs both brush and commutator life.
And clean up afterwards.
Absolutely critical. After seating, all traces of carbon dust must be meticulously cleaned out from inside the generator using compressed air or a soft brush. And a big warning: never use emery cloth or any abrasive material containing metallic particles.
Why not emery cloth?
Because the conductive particles can embed in the soft carbon brushes and the copper commutator bars, leading to shorting between segments, arcing, and serious damage. Only use fine sandpaper.
Got it. Fine sandpaper only. And the pressure exerted by the brush springs is also an important factor for proper operation, I gather from the text.
That's correct. The spring pressure holding the brushes against the commutator needs to be just right, within the manufacturer's specified limits.
What happens if it's wrong?
Too much spring pressure will cause the brushes to wear down excessively fast, and it also increases friction and heat. But too little spring pressure is also bad. It can allow the brushes to bounce or lose contact with the commutator, especially at higher generator speeds or under vibration.
Bouncing brushes, that sounds bad.
It is. This intermittent contact leads to electrical arcing, which damages both the brushes and the commutator surface, causing pitting and reducing the generator's performance.
How do you check the pressure?
Brush spring pressure is typically checked using a specialized small spring scale, pulling directly on the spring hook.
Okay. The chapter also briefly mentions flexible pigtails that are attached to some generator brushes. What's their purpose?
The pigtails. You'll see these flexible, low-resistance connections, usually made of braided copper wire, attached to most high-current-carrying generator brushes.
Why are they needed?
Their main purpose is to provide a reliable, low-resistance path for the electrical current to flow from the armature, through the brush material itself, and then out to the generator's external terminal or connection point. They carry the bulk of the current, not the spring.
So the spring just provides pressure, the pigtail carries the current.
Exactly. These pigtails ensure good electrical conductivity and also allow the brush to move freely within its holder as it wears down over time. Their connections need to be secure and checked for corrosion or damage, and they should never restrict the brush's movement.
Okay, makes sense. Let's now turn our attention to spark plugs themselves. They might seem like relatively simple components, but the chapter really emphasizes their critical role in engine performance. What is their primary function, and what are the key parts we should be familiar with?
Well, the spark plug's fundamental job is pretty straightforward. Conduct that high-voltage electrical impulse from the ignition system into the engine's combustion chamber and create a precisely timed spark to ignite the compressed air-fuel mixture.
Simple job, but critical.
Absolutely critical for efficient engine operation. Despite their seemingly simple design, the three main components you need to know are the center electrode, that's where the spark originates.
Okay.
The insulator, typically made of a hard ceramic material to withstand extreme heat and prevent the high voltage from leaking to the cylinder head before it gets to the gap.
Right, keeps the electricity contained.
And the outer metal shell. This houses the insulator and electrode, provides the threaded section for installation into the cylinder head, and forms a gas-tight seal to keep combustion pressure in.
The chapter discusses spark plug reach. What exactly does that term refer to, and why is it so important to ensure you're using a spark plug with the correct reach for a given engine?
Spark plug reach refers to the length of the threaded portion of the spark plug, the part that actually screws into the cylinder head.
The length of the threads.
Essentially, yes. How far it reaches into the cylinder head hole. Using a spark plug with the correct reach is absolutely vital.
Why?
It ensures that the tip of the spark plug, where the electrodes are, is positioned optimally within the combustion chamber for efficient and reliable ignition.
What happens if it's wrong? Too short or too long?
If the reach is too short, the spark plug electrodes might be recessed too far back inside the threaded hole. This can shroud the spark, leading to incomplete combustion, maybe carbon buildup on the exposed cylinder head threads, making future removal difficult.
Okay, and too long.
If the reach is too long, the electrodes could protrude too far into the combustion chamber. This is dangerous. They could overheat and cause pre-ignition where the mixture ignites before the spark occurs from the hot plug tip.
Ouch, that sounds bad.
It is. Or, in extreme cases, the protruding plug could even physically hit the piston as it comes up, or interfere with the valves. That means serious engine damage.
Right.
So correct reach is non-negotiable.
Got it. Match the plug reach to the engine spec. Now, spark plug fouling seems to be a fairly common issue in reciprocating engines. The chapter describes different types like carbon fouling, oil fouling, and even graphite fouling. What are the typical causes of each of these?
Yeah, fouling is definitely something mechanics look for. Carbon fouling, where you see dry, black, sooty deposits, typically occurs when there's an excessively rich fuel-air mixture.
Too much fuel.
Right, too much fuel relative to air. This could be caused by improper carburetor adjustments, a faulty automatic mixture control, maybe a leaking fuel primer, letting extra fuel dribble in, or just running the engine at low power settings for too long, where combustion temps are lower.
Okay. What about oil fouling?
Oil fouling looks different, usually wet, black, oily deposits. As the name suggests, it happens when engine oil finds its way into the combustion chamber and onto the plug.
How does oil get in there?
Usually due to worn or broken piston rings that aren't sealing well, excessive wear in the valve guides allowing oil to seep down the valve stems, or maybe leaking valve stem seals. It's often worse during periods of low engine speed or high manifold vacuum, like during descent.
Okay. And graphite fouling. That sounds odd.
It is a bit unusual, but it happens. Graphite fouling is usually self-inflicted, a result of improper or excessive use of graphite-based anti-seize compound on the spark plug threads during installation.
Too much anti-seize.
Yeah, or applying it carelessly. The conductive graphite particles in the compound can sometimes bridge the gap between the center and ground electrodes, or track across the insulator nose. This creates a low-resistance path that shorts out the spark voltage, preventing a proper spark from forming.
So use anti-seize sparingly and carefully.
Exactly, just on the threads, not near the tip.
Yeah. So the proper removal, inspection, and cleaning of spark plugs are essential preventative maintenance measures. What are the recommended procedures for these tasks?
Definitely. Spark plugs should be removed at the intervals recommended by the engine manufacturer. Use the correct deep socket wrench, designed for spark plugs, and apply even, steady pressure to avoid cracking the fragile ceramic insulator.
Okay, then inspect them.
Once removed, lay them out in order by cylinder. Carefully inspect each plug for signs of fouling carbon, oil, lead deposits, if applicable, any damage to the insulator like cracks or chips, and check for excessive electrode wear or erosion.
And cleaning.
Hard carbon deposits can often be effectively removed using a specialized vibrator-type spark plug cleaner or sometimes an abrasive bead blaster designed for plugs.
Like sandblasting.
Similar idea, but using specific media like glass beads or abrasive grit. Afterwards, it's crucial to thoroughly blast the plug with clean, dry, compressed air to remove all residual cleaning media. Any grit left behind could cause engine damage.
What about soaking them?
Soaking spark plugs in liquid solvents for extended periods is generally not recommended. Solvents can sometimes seep into the porous ceramic insulator material and cause problems later. A quick wipe with an approved solvent is usually okay, but not long soaks.
And after cleaning, how do you ensure a spark plug is fit for reuse? Setting the spark plug gap seems like a very precise adjustment.
Yes. Setting the correct spark plug gap, that's the distance between the center electrode and the ground electrode, is absolutely crucial for proper ignition. Too wide or too narrow, and the spark won't be optimal.
How do you measure it?
Always use a round wire-type thickness gauge that matches the manufacturer's specified gap for that plug and engine.
Why a round wire gauge?
Because the ground electrode often erodes into a concave shape. A flat feeler gauge won't give an accurate measurement across that curve, it'll bridge the gap. A round wire fits the contour better.
Makes sense.
Check the gap at several points around the ground electrode and make sure the ground electrode is parallel to the center electrode. If you need to adjust the gap, only bend the ground electrode, never the center one. Any plug with a gap significantly outside the specified range or with badly worn electrodes should just be discarded and replaced.
Good advice. Before reinstalling, anything else?
Yeah, it's also good practice to clean the spark plug bushings or helicoil inserts in the cylinder head using specialized thread chasers, not a tap, but a chaser to remove any accumulated carbon or dirt from the threads. Ensures the plug seats properly and torques correctly.
Finally, when it comes to actually installing spark plugs back into the engine, what are the key things to keep in mind? The chapter mentions the use of anti-seize compound and the importance of proper torque.
Right. Installation is critical too. First, always double-check you've got the correct approved spark plug type for that specific engine model. Check it's free from any physical damage, cracks, damaged threads.
Use a new gasket.
Always install a new copper spark plug gasket or sealing ring. Don't reuse the old crushed one.
Okay. And the anti-seize.
Apply a small amount of approved graphite-based anti-seize compound sparingly, and only on the first 2 or 3 threads of the spark plug shell, starting away from the tip. Be extremely careful to avoid getting any compound on the electrodes or the insulator nose.
Because that causes graphite fouling.
Exactly. Then, carefully thread the plug in by hand to avoid cross-threading. Finally, tighten the spark plugs to the precise torque value specified by the engine manufacturer using a calibrated torque wrench.
Why is torque so important?
Over-torquing can stretch the plug shell, potentially damaging the internal seals between the insulator and shell, leading to combustion leaks inside the plug. It can also damage the cylinder head threads. Under-torquing is also bad. It can lead to poor heat transfer away from the plug, causing it to overheat and allow combustion gases to leak past the gasket.
So Goldilocks torque just right.
Just right, using a torque wrench. And when reinstalling the spark plug leads, make sure the terminal sleeve inside the lead and the rubber seal are clean and free from damage. Push the lead firmly onto the spark plug terminal until it clicks or seats. Then tighten the coupling nut using the correct size wrench, being careful not to twist the elbow body itself or over-tighten the nut.
Got it. The chapter also goes into considerable detail about the maintenance of the magneto breaker contact points. This seems like a relatively delicate maintenance procedure. What are the key aspects?
Maintaining the magneto breaker points is definitely important and requires care. First, you periodically need to lubricate the small felt oiler pad, usually located near the breaker points assembly.
Lubricate it. With what?
Just a few drops of an approved, very light instrument oil specified by the magneto maker. But be very careful not to over-oil and absolutely do not allow any oil to contaminate the contact surfaces themselves or get anywhere else inside the breaker compartment. Oil on the points is a major cause of problems.
Okay, just the felt pad? Then what?
The contact surfaces themselves should be cleaned periodically using an approved electrical contact cleaner or solvent on a lint-free cloth or special contact paper to remove any oily residue, dust, or slight oxidation.
And inspecting them.
Visually inspect the contact surfaces carefully. Normal wear will appear as a dull gray, perhaps slightly irregular surface. That's usually okay.
What's not okay?
What requires replacement of the contact point set is seeing significant wear, like well-defined peaks on one contact and corresponding pits on the other, or a heavy buildup of transfer material on one contact. Deep pitting generally means replacement.
What causes that bad wear?
Different things. A frosted or white appearance often indicates an open-circuited condenser. The condenser isn't doing its job absorbing that arc. Excessive pitting can be caused by dirt or impurities getting on the contacts. Significant material transfer might be due to excessive spring tension, holding the points together too hard, or a faulty condenser, or even loose electrical connections in the primary circuit. Oil or grease contamination is also a common culprit for burning and pitting.
So point condition tells a story.
It really does. If they look bad, you need to figure out why, not just replace them.
And finally, the chapter briefly mentions the dielectric inspection of various magneto components. What does that type of inspection typically involve?
Dielectric inspection is essentially a careful visual examination of the insulating components of the magneto things like the coil cases, condenser housing, and especially the distributor block and rotor.
Looking for what?
You're looking for cleanliness, first off, but also any signs of physical damage like cracks, chips, burns, or evidence of electrical tracking, those thin black carbon lines we talked about earlier that indicate flashover has occurred.
What do you do if you find problems?
If these components are oily, dirty, or show signs of carbon tracking, they need to be carefully cleaned using only approved solvents that won't damage the insulating materials. Some materials are sensitive. In some cases, a protective wax coating that helps resist moisture and prevent tracking might need to be reapplied after cleaning following the manufacturer's procedure.
Any warnings here?
Yeah, it's crucial to use only cleaning methods and materials recommended by the magneto manufacturer. And generally avoid immersing components that contain internal capacitors, like some coils or condensers, as solvents could potentially seep inside and cause internal shorts and failure down the road.
Okay. The final section of the chapter addresses ignition harness faults and the methods for testing the harness. High voltage leaks seem to be a particularly challenging type of fault to diagnose in these systems.
Yes, high voltage leaks in the ignition harness are a common headache, frankly, and they can often be tricky to pinpoint reliably.
What causes them typically?
Moisture is a big factor, especially when it gets combined with contaminants like gasoline residue, oil, or grease that can accumulate inside the shielded manifold or conduits of the harness.
It reduces the insulation?
Exactly. It significantly reduces the insulating properties of the high voltage leads and can eventually lead to insulation breakdown and the formation of those dreaded carbon tracks.
What other kinds of faults happen in harnesses?
Common types include internal short circuits between the high voltage conductor and the outer metal shielding, maybe scuffed or cracked insulation on a lead allowing leakage to ground to the engine block, condensation buildup inside the harness manifold creating dampness, or sometimes just inherent flaws or aging in the insulation material itself that weaken over time due to heat, vibration, and ozone exposure.
And how do maintenance technicians go about testing the ignition harness to try and locate these often elusive high-voltage leaks?
Harness testing typically involves checking the integrity of the insulation surrounding each individual high-voltage cable within the harness assembly.
How do they test the insulation?
It's usually done by applying a specific high-voltage charge, often using a specialized harness tester or a megahometer, to the conductor at one end, while the outer shielding and the other end are grounded. Then, they measure the amount of current that leaks through the insulation between the center conductor and the grounded shielding.
Looking for excessive leakage.
Exactly. using a very sensitive microammeter or the megaharmonious scale. The measured leakage current or insulation resistance is then compared to the manufacturer's specifications for a good lead, new or serviceable.
And if it fails the test?
A lead showing excessive leakage indicates a breakdown in its insulation somewhere along its length and the potential for high voltage shorting or flashover under operating conditions. If a high level of leakage is detected, further testing and careful visual inspection might help isolate the fault to a specific lead, which would then need to be replaced. Or sometimes the fault might be in the distributor block connection where the lead plugs in. So, as we bring this detailed examination of reciprocating engine ignition and DC generator systems to a close, what would you say are the most critical things for our listeners to take away from our deep dive today?
For me, the overwhelming takeaway is just the incredible level of precision required and the critical importance of consistent, careful maintenance in both these seemingly different but equally vital aircraft systems.
Yeah, precision and maintenance. That sums it up well.
Whether it's the precisely timed Stark delivered by the almost mechanical ballet of a magneto, or the complex digital orchestration of FADC, or just the steady flow of power from the DC generator. Every component plays an absolutely crucial role in the safe and reliable operation of an aircraft.
Absolutely. And while the underlying technologies have certainly advanced over time, from purely mechanical magnetos to highly sophisticated electronic FADDC, the fundamental principles haven't changed that much. You still need to generate that essential spark reliably, and you need to maintain a stable electrical power supply.
Right.
The detailed procedures for proper operation and meticulous maintenance that are outlined in this chapter and in aircraft manuals, they're not just suggestions. They're absolutely non-negotiable for ensuring the continued reliability and ultimately the safety of flight.
It really gives you a profound appreciation for the intricate interplay of physics and engineering that's happening every single moment an aircraft is airborne, doesn't it?
It really does. Constant little miracles almost.
Yeah. It makes you wonder about the ongoing evolution of these critical systems in aviation. What future innovations might we see in aircraft ignition and electrical power generation? Will we move beyond FAD eventually? And maybe more importantly, how will the essential maintenance practices continue to adapt to ensure the skies remain as safe as possible?
That's a great question. Constant evolution, constant vigilance needed.
Definitely something to keep in mind.